So this is a challenge. We have essentially one person who hasn't been here in a long time, another person who's been here for the first time, other people who haven't been here for a long time. So more than half of the people who are here haven't been here basically at all. And I've been doing a ongoing, fairly cogently organized, though, and frankly, it's not cogently organized at all, conversation about the Big Bang. And from what I can tell here, I don't even know if 3 of the people in the room have heard of the Big Bang. So which I'm sure they have. But nevertheless, I'm just going to ask you a question. Depending on the height at which you raise your hand, how familiar are you with the Big Bang? Okay. Okay. So we have everyone's raising their hand. We have someone who's still holding their hand up because clearly he's the most familiar because he's been coming to this class for over 10 years. And then we have very familiar.
Well,
Question.
the fact is, I don't know if I sent you the article, that the Big Bang may not be Big Bang anymore.
So the Big Bang, I don't know, but yes, there was an article in today's paper about the expansion of the universe. Is that what you're talking about?
It was in a few weeks ago.
Oh, no, this one was in the Sunday Times. I mean, the Tuesday Times this week. So the Big Bang may not be the Big Bang anymore?
Yeah, because the math doesn't work out.
The math doesn't work. Well, okay. So there's a small modicum of controversy these days about the Big Bang, enough that it makes the newspaper from time to time. But in truth, while there is some controversy about the Big Bang, there is no controversy about the idea that there was a Big Bang. And we are the end products of all of that. It's been going on. It happened as a thing 13.8 billion years ago, and the universe was created out of pure energy. Not necessarily out of nothing, okay? There is that. This, by the way, is not news. The idea that the universe was not created out of nothing, sort of like a creation, is sort of old news. That news is about 40 years old. They just keep using the Big Bang and the word singularity as if the universe, there was nothing, and then suddenly there was something, and it was the Big Bang. So that's actually not a controversy. It's also not true. There was, as far as science is today concerned, the universe, there was a lot of energy, see, in a very small space. And then the Big Bang happened because that energy in a small space blew up to be the universe that we know and love today. But there's no controversy about that. The controversy is about some of the itty bitty particulars. One itty bitty particular that happened to be in today's New York Times was about the idea that maybe, and by the way, this is one of these wet dreams of cosmologists, that maybe we could get an answer to this question. The universe, as far as cosmologists have been concerned for quite some time, is probably flat. Now, as you can see by the shape of this room, it is not flat. Okay, it is three-dimensional. But I would point out that in this room, anybody who draws a triangle on this board, which is a flat board, any triangle I draw at all on that board, the sum of the angles on that board are 180 degrees, because this board is flat. If you try the same trick on a beach ball, you will discover that the angles don't add up to 180 degrees, they add up to more than 180 degrees. And the beach ball isn't flat, okay? So in a two-dimensional world flatness, you can curve this thing through a third dimension and get something round, and it's not flat. This room now is a three-dimensional room. If I could curve it around something that is, if you will, a fourth dimensionally like thing, then if I squeezed it the way I would squeeze this flat plane around a beach ball, I would get that the angles in the corners of the room aren't right angles. So the current controversy that is in today's New York Times is maybe the angles in this room aren't right angles. Maybe to the trillionth of a billionth of a quadrillionth of a degree, they're not right angles, and maybe this world that we live in isn't flat. Because the universe has been said to be flat for quite some time now. We've had quite a lot of evidence that it is. And now there's a thing in the Times. So you know what? I'm going to ignore that, because the article in the Times and other things I read said, yeah, that could be true. I'll get back to you later on it. And so basically, somebody has enough evidence to get their name in a publication to say the world is not flat. And as far as I'm concerned, good for them. As far as we're concerned, the universe is and always was and always has been a flat universe that is not curved spherically or hyperbolically, and so that takes care of that. There's another thing that Elaine was talking about, which is we got some wrong answers when we did the, not some wrong answers, some controversially different answers when we started measuring the Big Bang and started doing some numbers here and some numbers there. I talked about this in class for so much time that you know, many of you who have already been asleep in that class are still back basically asleep again in this class, because basically it was a long, tortuous, and by no means complete argument, which explained that if you look at the Big Bang, looking at the baby picture of the universe, you get one answer to how the universe is expanding. And if you look at another set of measurements, you get a different set of answers for how fast the universe is expanding. And if you try to bring those two groups of people into a room together, have them sit down, have coffee, and have them discuss their very, very scientific and very, very precise and multi-million-dollar answers to the question, how fast is the universe expanding, they will disagree, and they will not reach an agreement. See, in the past, these groups of people could sit in the same room and say, you know what, my measurements are here and your measurements are here, and there's an overlap, so guess what? The answer lies between the two measurements that we've taken, so we can all go home and be happy. But in most recent years, each team has gotten better at its measurements. Each team has gotten better at its measurements, and now this guy's numbers are within this kind of error, and this guy's measurements are within this kind of error, and they don't overlap anymore. So this guy's right, this team is right with its millions of dollars spent, or this team is right with its millions of dollars spent, but they will not begin to agree that the other one is right or wrong. So there's a controversy, and that stands. It isn't a big deal. It may be a big deal when we have an answer to why. It may be a very big deal. But right now, it doesn't change the fact there was a Big Bang. It's exploded for 13.8 billion years ago. I'm going to write that number down just in case you didn't see it before. 13.8, I think it's 2 billion years. We have a number on the age of the universe. It's that. It used to be a slightly different number. But over time, this number has gotten a second decimal place. And we know the age of the universe like insanely well. So there's no controversy. The universe exploded a while ago, and now it's doing that. Yes?
How did they come up with that number?
Well, that's a good question, and I refer you to the entire set of lectures that I did on the web, but I'm still going to answer it, okay? Nevertheless, I'm going to answer it. but not as well as you would like. Okay. For one thing, okay. So how did they come up with that number? One of the simple ways of coming back up with the number that's close to it is you look at the universe and how it's expanding. And basically, the farther you go away from here, where I live, the faster the universe is moving away from me. So, and it's very, very uniform. It's a straight line. Farther, faster. Even farther, even faster. Draw the line between it, it's a straight line. I'll show you the line. So this is the line. This line, every dot on this line is a galaxy. Every and so that is the dot. The vertical is how fast it's going away from us, and the horizontal is how far it is away from us. The fact that we know both numbers, both the speed and the distance of each of those galaxies, which is a major feat of undertaking, which is the subject of today's lecture. If I ever get to the subject of today's lecture, how we know this is the subject of today's lecture, how we know this graph. But nevertheless, right now we're just concentrating on what does this graph say. And it says the further that something is moving away from us, the faster it's going away from us. Further it's away, further distance, faster away. Straight line, you do the line, it turns out that the number, which is 72 megaparsecs per 72 kilometers per megaparsec per second. It turns out if you take that number and you turn it upside down, invert it, it gives you the age of the universe. Just like that. Okay? So it's and that's an approximation. It doesn't give you this beautiful number. It gives you a number like 13 or 14 or 15 or 17 or whatever. It gives you a number that's fair, but that's not the way they do it. But it's just like, so for years they had a number, and just now they get a better number. The fact is that if I didn't bother you with telling you that it was so accurate, I could say that this is the way we got it. Simple. It's right there on the screen. That's the answer, but the answer instead of being 13 is like 17 or something. You know, and I tell you that's the age of the universe, and you'd be happy. Just that you're maybe not happy with the extra decimal points. Yes.
Just inverting that 72 kilometers per megaparsec per second, it is a parlor trick to give you the age of the universe. That just seems like a parlor trick. It doesn't seem to be proof of.
Well, no, it's actually you have to. It's not a parlor trick. If you think about, if you know how fast stuff is expanding away from you, and the faster the better, then when you think about if you ask the question, well, gee, when was it all back together again? It's still right on this screen. It tells you that if you imagine it was instead of 17 billion years ago, if you imagine it was 5 billion years ago, each of these dots would be closer to here, right? They'd be closer to here. You just keep, that's the parlor trick, just keep dividing until you get some really close and down and small enough that you're happy, and then you get the age of the universe. It is that number, inverted. You know, it's just, the units are not the same. The 70 also includes a word called megaparsec. And a megaparsec is something like a light year, but isn't. It's 3 light years and more. And light years is not a unit of anything. It's something we made up, you know, having to do with light and years and how long the Earth goes around the sun. Has nothing to do with it. You want to measure it in seconds. Okay? And the answer you need to get is seconds. And that doesn't seem right, because kilometers per second, there's a second, there's a kilometer, and then kilometers per second, and then per megaparsec per second. The megaparsec is a distance, the kilometer is a distance, they cancel, so that unit is gone, and now you have seconds. You have seconds in there. So you want a unit of measurement that is in seconds and seconds alone. And that's what the Hubble constant is. It's in seconds.
So to me then, the problem lies in defining adequately a unit of something that measures what we're trying to talk about. Because if you have a unit, megaparsecs isn't it, and this isn't it, and that isn't it, we really need
Yeah, there's only
an
one thing.
adequate
It's in
definition
seconds.
of a
The
unit.
universe, this billion years, can be turned into seconds. A year is, if I'm not mistaken, 3 times 10 to the 7th seconds. So you can take that, multiply it by 3 times 10 to the 7th, and you get, and then by another factor of 10 to the 9th, because that's billion, and that's the age of the universe in seconds.
But isn't there probably a better unit measurement than seconds?
No, seconds is good. We don't have anything better. It's arbitrary, but it's our arbitrary. Okay, there is no natural unit of time. Okay, there's no. I mean, there is a natural smallest amount of time, but there is no natural unit of it, and it's still expressed in seconds. So the answer to this question, how do we get that number? We actually have a theory, and I did it on the screen. There's a couple of knobs. The theory gives you a graph, and then the data gives you data points. And so you take the theory, which basically can be fine-tuned by a series of 6 knobs, and you turn the 6, and I did this in class, so you turn the 6 knobs till you can get the theory to match the data, until you've got it all done, and when you finish turning the knobs, that number comes out. So it's like magic. It's beautiful. It's like oh, right, of course, the universe is this age, because otherwise the theory would be wrong. So you either challenge the theory, which is this hand. When I was talking about stuff, it's this hand. Okay, a lot of people, millions of bucks, hundreds of people, this hand, those knobs, that number, versus what I came to talk about today, which is the other part of it. This hand, how they got this stuff. Okay, but to begin with, since there are so many people who don't know about the Big Bang, I encourage you, before I go wandering into space that you don't care about because you didn't understand the first part of what I just said, I encourage you to ask a silly, stupid question that you think is silly and stupid. I will, of course, value it highly. So if you could simply ask me something that you don't know about the Big Bang, we could try to recover from the fact that I'm going to teach you a boring thing that was based upon the 5 or 6 previous lectures. Question, Howard. Howard, you've been here forever. How could you have a question? You're going to have a statement.
There's something ridiculous about this whole thing, and the ridiculous thing is that this amount of energy that you say was there initially instead of nothing was smaller than one atom,
Right.
supposedly.
Right.
So something that was smaller than one atom existed
Yeah.
there for no particular reason.
For no particular reason.
That's myth.
No. It's actually okay. So that's close to a question. It's a statement, which I expected, but nevertheless, it is a question. How could the universe have started from something that is, like as small as an atom? Although, in truth, it doesn't have to be quite as small as an atom. It can be a little bigger, and have all that energy, and all that energy is compressed together, and it's going to form the universe. And I ask you the question. Actually, I've been asking myself this question because it really is the same. I have that same question, so it's not like I'm going to dismiss it as oh, that's silly. No, it's profound. How can the universe have started from really concentrated amount of energy, like in smaller than this, and it blows up to be the entire universe that we observe, and probably a lot more than we don't observe? How can that be? Okay, I grant you that's really hard to get your head around. But here's something that's also hard to get your head around. Okay, the temperature in this room is 72 degrees Fahrenheit. Okay. You can get your head around perhaps the fact that we could globally warm this planet to above the boiling point of water if we wanted to, and we might be well on our way to doing it because it's not against the laws of physics. It's just a shame. But you're not going to get your head around that. But you do know that out there in outer space, things are hotter than this. Okay, but can you get around the idea that the planet Venus, the surface temperature on the planet Venus, is hot enough to melt lead? Does that work out for you? It doesn't seem right. It seems like the world should be a little bit more like we experience it, on our basis of our own experience. Yes, Elaine?
I read that Venus originally had oceans and was not hot.
It's possible. I spent a year of my life working on the idea that Venus originally had oceans and was not hot. It's not provable, but it's a likely scenario. We haven't found the ocean basins on Venus to prove that point. So there's no evidence. It's just a very good hypothesis. It makes sense. The sun was cooler. Venus wasn't as nasty as it is today. There was less carbon dioxide in the atmosphere. All is possible. It's possible. Yeah, so maybe Venus was our friendly home years ago. But can you imagine the boiling point of water being the melting point of lead is the surface temperature of the surface of Venus, and the pressure is so high you'd have to go down 1,000 feet in the oceans to experience the same level of pressure. You can't imagine that because it's not our experience. What about the center of the sun? Okay, you know the center of the sun is hot, but you can't imagine how hot that is. You just basically accept it. Millions of degrees, you've been told. Okay, and you need that because you're busy making busy making sunlight out of fusion energy. So clearly, it's got to come from somewhere. And you've met the hydrogen bomb. You know that's a pretty nasty project. So you know that millions of hydrogen bombs are going on in the middle of the sun all the time, and you can accept that, even though it doesn't have any, relationship to your being. Yes.
But we can extrapolate because the sun has surface heat.
This is not extrapolation. Thank you.
No. But I'm saying that since we know that the sun, if we look at the pictures of the sun, the surface is
5,000
degrees, whatever.
5,000.
Then you have
5,000.
Okay, 5,000. Then you have darker places, which are sun flares, different temperatures on the surface of this boiling hot surface. So we can know that other temperatures exist even among the hotness of the sun. Because the flares are a different temperature.
Yeah, but literally the stuff that's going on the surface of the sun, not interesting if you're talking about the center. Has nothing to do with it. If you're calculating the temperature in the center of the sun, you didn't go to the school room. You didn't take the class. The surface of the sun is the class that you missed when you are studying stellar structure, which is interesting. A course that I took once. Okay, so I took a course in stellar structure, and the thing that made it exciting, he was a very brilliant man, and he derived the temperature at the center of the sun on the back of an envelope, literally in front of my very eyes, and he got a temperature which was close to the temperature that was accepted by scientists at the time, within a factor of 2. And it was millions of degrees. But you don't need the temperature at the surface of the sun to start.
No, but I'm just saying that is an intriguing phenomenon that tells you that temperatures, vast variance in temperature exists in the same place.
Yes, certainly. So anyway, my point though is so you can't imagine the temperature of millions of degrees because that's really crazy. You can just stipulate it. You can't imagine it. But what about when a star explodes? You've heard that. You've heard they do that. When they do that, the temperature at the center of the star is billions of degrees. Are you good with that? Can you do that? You're objecting to something that's bigger than that. I'm saying is exactly where did you get your experience as to what's okay and what's not? I think billions of degrees is someplace you should stop and say, no, I can't do that. That's it. That's too much for me. Temperature is too much. So you say, well, I'm sorry, I'm not happy. The universe couldn't possibly be this energetic. The temperature couldn't be as high as all of that. And in fact, it turns out it's not. Because Because if the universe had ever been as hot as you think it was, the universe would be filled with these things called magnetic monopoles, which are, you get a bar magnet, it's got a north and a south. Imagine you could go into a store and just buy a north. Okay, right? There's no such thing, and the universe is not filled with any of these norths and separate souths. Guys selling north, guys selling south. The thing, if they did, they'd have a north and they'd have a south, and they'd have a mighty crash because the people selling norths and the people selling souths would get together really fast in a fairly nuclear explosion, and it would all disappear. And so would the Earth at the same time. The universe doesn't have magnetic monopoles. And because it doesn't have magnetic monopoles, it also says there was a time in the ancient past in which the universe wasn't as hot as it could possibly be. It was a little colder than that. So there's actually a limit on how hot the universe was. It's a ridiculously high number, but it's still a number you can't get higher than. So it's okay that the universe is this one little place that was ridiculously hot. You just object to ridiculously hot. And I'm simply asking you, on what basis do you object to ridiculously hot? Because we need ridiculously hot to invent the universe. If you don't like it ridiculously hot, I suggest you go and figure out another way that the universe could have been created. Because in the past, it certainly was ridiculously hot. You just say, but there's only a limit as to how big ridiculously hot it could be. And I say, yeah, no magnetic monopoles, so there is a limit. Anyway, so the universe was created in a Big Bang. We could spend months on this. So if you want to ask another question before I begin the actual lecture that I came to do, which I often never do, but if you do have another question, please ask.
Just begin.
All right.
All of this is not making too much sense.
It's not making too much sense. What part isn't making too much sense?
Any of it.
Brave woman.
I love this part. I love this part. So for at least one of people out there, it's not making sense. Hopefully, it's not making sense for the rest of you. But anyway, let's begin. Okay, so the subject of this class is my right hand. The guys on the left hand got their due in many classes. Now the guys on the right hand are trying to get through this miasma of side effects asides. So, those of you who have been in this class before may have seen this picture on the screen many times because I never got to discuss it. So this is like the universe, if you will. The universe is in this picture, or at least parts of it are. Let me show you the universe.
There's a class in here.
Hold on. The universe is like there, okay? Whole universe, everything you ever wanted to know about the universe right here on this picture. And the thing that makes it incomprehensible, because you can look at this to Kingdom Come and not understand it, is that it's designed to be in steps of 10. So the first step I take is 1. The second step I take is 10. The third step I take is 100. The fourth step I take is 1,000. And it doesn't take more than about, if you're using steps, just steps like that, I think it doesn't take more than maybe 20 to 25 steps before you reach the end of the universe. And because 1 foot times 10 to the 25 is maybe I need 10 to the 30. But by the time I've just introduced a few factors of 10, I've gotten to the end of the universe, which is why you start out here, and there's the sun, and there's the sun and the Earth and the moon, and pretty soon you're past the planets, and you're into the stars, and then after a while you're past the stars, and you're into the galaxies, and after a while you're past the galaxies, and you're into clusters of galaxies, And then after that, you're into clusters of galaxies, the filamentary structure of the grand scale structure of the universe. And if you keep on going, you more or less get to the end of the universe. I mean, or the beginning of the universe, depending on your point of view. Because the further you go back this way, further back in time you go as well. So it's fair to say the end of the universe as well as the beginning of the universe. So that's the whole universe, okay? And the thing is, the question is, okay, sir, how do you know this? Sir, you have a nice pretty picture here, but how do you know where these things are? Because, let's see, how do I know where you are in this room? Well, that's very simple. I have two eyes. I know how big you are, no bigger than 6 feet on the average. And so my brain is very good at this. Even with one eye, I can pretty well figure it out. 2 eyes, I'm great, because I've got stereoscopic vision, and I can figure out where you are. When you look up in the sky with a telescope, clearly you're missing one eye, okay? And also, since you've never been there and shook hands with any of those things, you don't know how big they are, and you don't know how far away they are. So anything could be possibly true, and you have to figure these things out. So this is what you do. You set the entire human race at the problem, okay? And over time, a few people get some good ideas and come up with the right answers. Do you remember Y2K? Do you remember it didn't happen?
Right.
Do you remember why it didn't happen? No. The reason it didn't happen is everybody in the human race got together and said, I think we need to fix this. So everybody worked on the same problem and it was solved. I think that's the real answer to why Y2K, why we survived it. Otherwise, I don't think we would have. So the answer to how far away things are in the universe is the result of not just one person's studies and activities, but the work of thousands and thousands of people throughout the ages who have increasingly gotten a better answer to the question of how far away everything is. Started early on with a guy named Aristarchus who was able, can you imagine this? It's BC sometime, 200 BC. And this guy figures out that, first of all, he goes with, hey, the sun, it's a star. Let me see how far away it is. And he does this sort of thing. He looks at the moon, he looks at the sun, he looks at the moon. You can't stare at the sun so well, so he didn't get it right, but he did. It's not a right angle. It's a little bit off a right angle, but if he did the right number, he blind himself. So he didn't get it right, but he did get 5 million miles to the sun. That's insane. He knew 5 million miles. And then he would look up in the night sky and say, you see all those stars? They're suns also. I know how far they are away because they're dimmer. So he came up with the fact that the stars were at light years away. Insane. He knew in 200 BC, he knew how far the stars were. He got it, royally wrong, but he knew the universe was big. You don't hear that story in school, that the universe was big. You think that Columbus was an idiot and didn't go to school and didn't know how big the Earth was, when in fact everybody who knew anything at that point knew how big the Earth was. How stupid can you be? It's 1492, 15th century, and they don't know how big the Earth is. You can see the shadow of the Earth on the moon, for God's sakes. You can walk a distance on the Earth and see that the sun is not overhead here, but in the same place, a few hundred miles away, the sun is overhead. You can see. How far did I walk? Well, I walked, 200 miles. You ask your friend, is the sun overhead here? Yes. Well, it's not overhead here at noon. So you can figure out the angle, you can figure out how big the Earth is. It's not rocket science. It's ancient science. What Columbus got wrong, I read this today because I needed to know this for this. I was going to make this point, and I realized I was going to make this point. What did Columbus get wrong? Columbus knew that the Earth was, we know it's 25,000 miles in circumference. He knew it was 25,000 miles in circumference. The problem is he didn't get the thing called miles right. He was using somebody else's version of what a mile is, and there were, if you will, Arabic and Roman miles, and he picked the wrong mile, and his mile was about 60% of what our mile is. Of course, he wasn't using miles; he was using whatever unit he was using. But his mile was 60% of our mile. So when he knew that the Earth was 25,000 miles in circumference, they were shorter miles. And so he could figure out that you could get to India if it was shorter miles. So we don't make that mistake anymore. Well, hardly. We did actually land a spacecraft on Mars, and the British people used the metric system, and the Americans used the English system, and it crashed. And after it crashed, they figured out why, because the things that they wrote back and forth to each other were in units that each of them interpreted differently.
Laird,
Yes.
Howard's birthday is Columbus Day.
When is Columbus Day?
He's Columbus Day.
You know why they don't name it Columbia instead of America?
Yes.
Because this.
America's Vespucci.
Because
Yeah, but what did Americus Vespucius do? He made maps, and every map he made, he put his name on it. And Columbus didn't make maps, so when they looked at the maps, it was America's map. And
Because
then-
it was made by somebody called Amerigo.
Amerigo, I think, right, to be more specific. Okay, so the question is, how do you know all of these things, the distances to the places, to all these places? Because, I mean, every one of these things on this graph are placed here by someone who knows how far away they are. You know, every one of these things is a certain distance away. Yes.
Hey, I still don't understand something you explained before, but if you would like to say it again, why is the universe finite instead of being infinite?
Why is the universe finite instead of
Yeah,
infinite?
finite. Yes, why is it? I mean, how do they calculate that at a certain point it ends?
Okay, so you'll be happy to learn that there is no answer to that question, but I'll reverse it. You said, how do we know it's finite? And I'll rephrase it. Do we know it's finite? And we do not know it's finite. So then you say, well, if it's not finite, then is it infinite? And I would say to you, we do not know if it's infinite.
Yes.
Right. 9 out of 10 cosmologists will go with infinite just because it feels so much better. I mean, if it's finite, then you have another set of questions that you really want to ask about finiteness. You know, how big is finite? And we can't answer that question. So it's really better, and it's so much better, and it's so much better to simply say, listen, for God's sakes, the universe has always been, it always will be. What's wrong with that? It gets rid of a creator immediately. And the Big Bang, if you do that, you go, wait a second, there's a Big Bang. How do you account for that? You said it was been around forever, and now you're telling me that it's 13.8 billion years old, so that looks pretty finite to me. So all I got to say to you is, yeah, but you know what? There was more than one Big Bang, and they're going on all the time. Right now, for example, there's another universe being created in the infinite void out there, okay? Like popcorn, multiverses all over the place. And so in this infinite universe, there's infinity of universes. There's no reason that our sort of young one at 13.8 represents anything more than just one of them. Some of them are older than ours, some of them are younger than ours, okay?
That's conceivable.
That's conceivable. Wait, Howard.
May I add something
Yes.
else? What is the relationship of the wall with the wall of no return? What's the wall of no return?
The wall of no return. Okay, I'm not sure what you mean, but you see this thing has a wall?
Yes, that's right.
Okay. So that's what they call, this is not the universe. It is colloquially the universe, but is in fact, the right word for what you're seeing on the screen is the observable universe. And we haven't seen everything out here to the very end. We just know that we could if we had better telescopes and more expensive telescopes. We could see further and further. But no matter how good the telescope is, we know there's a certain distance beyond which we cannot, will not ever see. From here to here is, and we have a number for this, which is really crazy. Traveling at the speed of light, you would expect that the thing that's furthest from us is 13.8 billion light years from here. So that you expect that that's 13.8 billion light years. The radius of this sphere you would expect to be that, but it's not. It's 45 billion light years. The observable universe, the wall is constructed at 45 billion light years from here. And the laws of nature prevent us from ever seeing beyond it. And the reason for that is because space is expanding, which of course I didn't describe that until just this split second. Space is expanding. And there's a place where, beyond there, space is expanding so fast that the light from beyond here will never reach us, because by the time it gets to us, space will have expanded so much that the light will be further away from us than it was to begin with, and it will never reach us. So that's where the line is. It's not a real line. It's just, you can't see this. You know, if there could be another universe hanging out nearby, just down the block. We have no evidence for it, and probably never will have evidence for it. Is this a question or a statement?
Question. You know that I believe in a higher power, but my question is, you're not allowed to ask this question, but I'm going to ask it anyway.
You're allowed.
What is the universe expanding into?
Aha.
That's the question, so don't ask that
Well,
question.
no. It's what is the universe expanding into is fair, but I haven't practiced answering this question well enough to give you a satisfactory answer. Okay, but I have a better answer than I used to have. Okay. So I read this paper on what is empty space. Okay. Try to imagine empty space, nothing in it, completely vacant. All right, that's space, nothing. So when you go to empty space, nothing, it turns out the empty space is full of stuff.
Yeah.
For example, and you know this, dark energy is in empty space. So empty space isn't empty. So that's not an answer to your question, what is the universe expanding into? So I'm not really going to satisfy you with my next statement, which is, it is creating space as it expands. I do not like that answer well enough. I'm sure you do not. But for the time being, that'll be my answer. I'm going to keep working at this answer until I get up something that I feel will make me feel a little better about it.
It's actually very good.
What?
Just the idea that you create space and you expand is a very good idea.
Yes. See, that's part of the answer. Okay, you have space, okay. Here's Einstein. Einstein said in his, he wrote down the general theory of relativity. Turns out the general theory of relativity says if you don't muck with this, space, in the absence of gravitational anything, don't leave it empty. Just leave it empty. Space, leave it empty. Expands. or contracts, because he didn't know which. So he threw in this thing called the cosmological constant, which kept it from doing either. But if in the absence of throwing in a little fudge factor, the general theory of relativity, the equations, which by the way are the only thing that you're allowed to believe in. And that's, you can't believe in anything I say. Okay? It's only Einstein's theory of general relativity. Those equations are the story. I'm just the guy who's telling the story from having been told the story by other people who read the equations. And the equations say space expands. But if, Howard, there's the answer. Space expands. You mean this space expanded into this space? And that doesn't bother you? You want to know what space is expanding into. How about the fact that space created more space? Space. In other words, something that was here and something that was here, and it was minding its own business, is now here. Okay? And it didn't do anything. It was just doing nothing. Imagine a point that has no gravity and another point that has no gravity, so they're not attracted to one another, you know? So they're just sitting here minding their own business. And then 1 billion years later, they're over here. That doesn't bother you? It should. You know that space expands. You've been a aficionado of Einstein's theory of general relativity forever, and yet you never question this one. So why do I need to explain to you what space is expanding into? It's infinite. We said that, okay? If you go with infinite, and if you go with that these things can separate all by themselves, you know, because space wants to do it, then I don't have to answer your question. Space is infinite, and things move apart from one another. It doesn't expand into anything, because infinite, hard to get your head
You're
around.
saying it creates itself. It
Yes.
creates more of itself.
Right.
Which is a perpetual motion something.
I don't know that that's exactly true, because I don't know that you could put a spring between these 2 points, okay, and have them create a tension which could be used to create a force that could be used to create work, and nothing would have been done except space would have created. Maybe you did in fact invent the perpetual motion machine we've been looking for all these years. And I agree with you. There needs to be, that question needs to be answered as well. Okay, so good questions, Howard. These are good questions. Yes, in the back.
There are so many contradictory things in what you're saying that it's hard to understand.
Give me one contradiction.
Well, how can they give a definitive number
Right.
for the size, what they think of the universe, based on the observable universe, based on speed of light, when we know now that there are things that we do not see everything because it's not all light.
Okay.
It's dark.
First of all, you did come in before
Yes.
I wrote this number on the board.
Yes.
Okay. After I wrote this number on the board. I did have a little bit of conversation about that, but you've been here for years, so it's fair that even though you didn't hear my little small synopsis which tried to explain this, but you have been here for so many lectures, or at least you've been late to so many lectures. Thank you.
That was so mean.
That was so mean. But no, I understand. But you have to own that there's a certain consistency. Anyway, and it wouldn't happen any other way. The fact is that that 13.82 billion years is a well-established number at this point in time. You would agree with that? I mean that it's been derived. People are happy with it. It's been accepted by scientists at this point. The number's been moving around. When Carl Sagan was giving the Cosmos series, he was saying numbers like 17 and 15, and he didn't know. You know, the number's been moving around, but it's been settling down, and nobody's challenging that. Maybe the second decimal point might be being challenged, but not the first, anymore. But again, I wasn't answering your question. You see so many contradictions. All I can say is if we address the contradictions one at a time, but we need to be, you actually, when you spoke before, you mentioned a couple right off the bat. So if you could say just one contradiction, name it, because I don't have any contradictions as far as I'm concerned. So I would say that you conflated a couple of things together and then came up with a contradiction. So say one contradiction.
The concept of measuring anything according to the speed of light, when we know now that there is not light that we can measure right now.
Okay, computing something according to the speed of light when we know that there's light that we can't measure right now. That is a conflating. Okay, that's a conflating. Okay, this number was not measured using the speed of light. It was used using a theory about the creation of the universe based upon Einstein's theory of general relativity, and they came up with a series of equations, which then we twisted the knobs on the dial until we came up with that. That didn't have anything to do with the speed of light, and the speed of light, what you were talking about in terms of not knowing anything about the speed of light, you're talking about this wall here, where we don't know anything beyond it. Is that what you're talking about? It has nothing to do with that as well. So I'm going to just have to leave it for the time being. Yes, yes.
The Big Bang that happened 13,082,000,000 years ago, was the sun and the other galaxies were there before the Big Bangs? And if so, how come the universe is situated exactly in order for us to survive, distance from the sun and from the moon with gravity and, with the rest of the galaxies?
Okay, so that's great. That's a great question. How come was the sun and the galaxies around at the time of the Big Bang or certainly thereafter, and how come everything is so perfect right now for us to be here in this world? So okay. The Earth is 4.56 billion years old. The Earth and the Sun, both, are 4.56 billion years old.
From the Big Bang?
No, since today. In other words, it's the 4.56 billion year birthday of the Sun.
Okay.
It's 13.82 billion year birthday of the universe. Okay. So the Sun has been around for a short period of time. The galaxy in which the Sun lives has been around for maybe 10, maybe 11, maybe 12 billion years. Okay, not forever, and not as long as the Big Bang. So the galaxy in which we live, the Milky Way, was born somewhat, let's say, 1 billion years after it. In that galaxy, there were stars were formed, and stars were born, and stars blew up and shot their gases out into the interstellar medium, only to be reformed again into stars. And that sort of thing happened once or twice or 3 times. We happen to be the product of the explosion of maybe 1, maybe 2, and maybe even 3 supernova explosions that happened between the 10 billion year marks, let's say when our galaxy was built, and the 4 or 5 billion year mark when our sun was built. So there was a lot of stuff going on. So we exist in this so the perfect thing that happened was, if those things didn't happen, the stuff that you're made out of, which was all made inside of exploding stars, every bit of it, except for the hydrogen in the water in your body, every bit of else of it was built inside of a star, you wouldn't be here. Okay? So we happen to be at a planet that just happens to be at the right place, at the right time, with the right everything. Right everything. And if you happen to, the more you know, and I know a lot about this, the more specifically magical it becomes. There is no way that this was a class of religious fanatics, And I was here to try to convince those skeptics who are among the class. I could make a very good case for the existence of God based upon, you think the universe is really magical. Well, it's a lot more magical than that. And I could spend days and weeks just rolling off all the amazing things that had to happen so you could be sitting here in this class right now. I mean, I can't.
How'd that happen?
Right. So I'll tell you. Evolution made you, okay, and we happen to be the lucky ones because here's a number that you might like. See this picture here? This picture contains the whole universe, observable universe. In this picture, if the guy who drew it was precise and not just magical, he could fill in every little dot here, and he would need a little dot over here, making little dots. He'd have to put 2 trillion galaxies into this picture. 2 trillion galaxies like the Milky Way. You want to know why you happen to be here, sitting here at this lecture right now? Well, there's 2 trillion other chances in the lottery that you could have been in another galaxy in which maybe the same thing happened. We don't know the frequency of it. That's why we go to Mars and other places. We want to know what the frequency of the creation of life is. It's the most burning question, because once we know that, we know how many of these places in the universe have life. And intelligent life would be some other supposition that we'd have to come up with in order to explain us here now. But that's why I'm telling you, if you were a religious class, it would be so much easier. I could explain to you the unlikelihood of this. I would leave out the 2 trillion stars, galaxies. They're not stars, they're galaxies. And each galaxy has 100 billion stars. Multiply those numbers, they're meaningless. A trillion is a meaningless number. You could count to 1 trillion, it would take you 30 years. 1, 2, 3, never get to 1 trillion. So, trillion galaxies. Yes, Barbara?
Did you say that the sun and the planet are the same age?
They are. The sun and the planets are the same age. Give or take about 10 million years, yeah. Which, by the way, is over here in the third decimal point, The age of the
saying, give or take, which gives us a gap of a few years for the planets to form after the star, our
Right.
sun, had settled down a bit
Yeah.
so that the other debris around it could coalesce, could come together.
Right. It happened at a very quickly. The gap in time between this formation of the sun and the formation of the planets is millions of years, not billions of years. And astronomically speaking, it's an eye blink. The sun and the planets form at practically the same time.
But not exactly.
Not exactly. And the planets are not a happy place to be for at least about 1 billion years. So you got a lot of crap going on. But they are being formed. And every star has planets. More or less, every star has planets, and we can see that there are lots of them. Every star has lots of planets, because the formation of a star necessarily involves a formation of a flat disk around that forming star, and that flat disk ends up forming planets. It's just that way. They knew this before they knew it in the 18th century, before they could even look. Yes.
Not long ago, scientists announced that they found a planet far away that resembled in its serendipities for human beings something approaching what Earth has.
There has never been. They've announced planets all the time. Just when you see the announcement of an Earth-like planet, just skip it. Okay, just skip it. They're lying to you. There hasn't been anything close to an Earth-like planet. Neither has there been a spacecraft capable of detecting it. there's no experiment current flying or ever flew that is capable of detecting an Earth-like planet.
So then this is just a myth, just a fabrication?
No, it's something to draw your attention. So if you don't mind a planet that is twice the mass of the Earth, flies around its sun in 7 days, keeps one face to the sun at all times, and but the temperature on the surface of this planet is so nice for life. It's bullshit. It's just a story. If you're going to build an Earth, it's got to be going around a sun-like star. A G2 star is our kind of star. Taking a year to go around. You don't want it to be a different kind of star because those are nasty. You don't want it to be a bigger star because they blow up or they age quickly and die. You don't want it to be a smaller star because then you have to be closer to it. And if you're closer to it, then all sorts of stuff can happen from the star itself. So you want to be this distance away on an Earth-like planet which has just the right amount of water, because you do not want to live on a planet that's made of only water. What fun would that be? Dolphins have a good time, but they're never going to space travel. So if you're talking about intelligent life, there's nothing that they're going to discover in your lifetime, remotely. Even the proposed Carl Sagan telescope would, at best, do a poor job of answering this question. We have to do a much better job. It's for the next century to do this work and maybe begin to answer the question. They're just going to hype you. So, whatever.
Nothing to do but annoy us?
Yes.
Or trick us?
Right. I gave a lecture in which I read an article from the New York Times and explained to you why it annoyed me. It's on the web. Why this article in the New York Times annoys me, because I highlighted every bit of hype in the article. It said, disclaimed, it said something that was hyperbolic, and then it disclaimed it in the second sentence. You had to read the second sentence. Yeah, they're not going to find anything. Guess what? I never got to my lecture. Again. I'll tell you what my lecture is going to be, and then we can maybe discuss it next time. I picked this graph so it would be meaningless. Okay, so do not try to derive any meaning from looking at this. But the point is, it's the extragalactic distance ladder, and it says that these are the stepping stones to figuring out how far things are away from us. And there are different methods, as you can see. Each one of these boxes is like $1 million worth of work, or maybe $10 million worth of work. And I could show you a different graph, and I will explain some of those things. I will not, I promise you, explain many of them. But here's another one. Here's another picture. I like this one better. Because what's true in this graph is you see various methods and how good they are. This method is good for this distance, and this method is good for this distance. But notice they overlap. So that one of these methods can be built on the steps of another one of these methods to build up the ladder. One tells you a distance, but then it helps you with the second rung, because the second rung is standing on the first. So we'll talk about the rungs. That's what I eliminated from this conversation. I probably did it because I put more of you to sleep. I like the questions rather than the answers, rather than my answers. So on the board, here is the attendance sheet. If your name is not on it, write it legibly so that somebody else can read it besides yourself.
Here.
And I have a pen.
Here's a pen.
Okay. And if you have an email address, please add that email address. It's sorted by your first name. If you have an email address, put that down as well, writing legibly so it can be read. Because the way I tell you that the class is canceled is by emailing you. And if you've been to the class recently but have no email address, I will call you. but I tend to call people who have been here more than once recently, who have no email address. So put it down. The next class is next week, but there is no class on the 24th or the 31st of this month. Thereafter, it goes on forever.
December.
December. I said this month, but I meant next month. Yes.
Piggybacking on what that chap asked, can't we say we're extremely fortunate to be here, to be on a planet like this, to be alive, to have the neurons and positrons and so forth that we have?
Yeah.
Because there's such a good chance that we all could be not here.
Right. No. So when I'm teaching the religious version of this class, okay, I think the religious version of this class, I'd like to make a long, very, very, very long list of the reasons why we shouldn't be here. There's a molecule called ATP, I think it's called, that is generated in the mitochondria of our cells that is necessary to give us the energy that we have to do anything, otherwise we'd be slime molds. So this molecule is one of the most beautiful molecules ever invented. But remember, you're a religious class, by God. So there's so many things that God did so well when he was designing the universe that there's no possibility that there was not a creator. It had to be. This place is too perfect. But you can still argue, for those of you who are not religious, that all of this occurred simply randomly for the earth being created in the first place, and naturally according to the laws of physics, and then by evolution to get us to where we are today. It doesn't need a creator as far as I'm concerned. But if you want to take what I'm saying and argue the opposite, you're welcome to it, and you can do a very good job. So, I think every time I think of something, for instance, I look at my grandchildren, and their brains are growing, and there are neurons in my brain that are saying, aha, I have to find my way across the brain to the other side to hook up this piece of information with this piece of information. So I'm going to grow a neuron, and I'm going to know exactly where to go. They don't know, to this day, how the brain organizes itself. And imagine, it's all done in the DNA. DNA says, hey, I got an idea. You're going to need some prefrontal lobes over here? Good. We'll put them here. How does the DNA do that? How does the DNA is the most amazing structure in the universe, far more amazing in some ways than the universe that I talk about. The biology of biology period is a lot more, you can't believe they did that kind of thing. The universe really just didn't require evolution. The universe just gets there by simply having a good set of laws. Hey, good set of laws, you guys do that, follow the laws, you'll be good. Evolution says no. We're going to naturally select you to be who you are today. That's more insane as far as I'm concerned than trying to invent the universe. The universe is crazy. I mean, there are protons and neutrons and electrons, who thought of that? But once you got that idea, it's easy to invent the universe compared to inventing one of us, I think. Well, it did take 4.5 billion years to invent us. So, and we're pretty amazing creatures. There's a book I just finished reading called Sapiens. Sapiens is a fantastic book that will put who we are as a species in its proper place. And there's some really amazing things that I never thought of about why we're as amazing as we are. And it's the name of the book, Sapiens.
Who is the author?
Oh, it's some person with three foreign names that I don't recognize.
Harari is Israeli.
Yes. Oh, he's Israeli?
Yeah, I think he lives in New York.
Yeah, he's amazing. To read that book, Sapiens. It's only 800 pages. You will love every page.
800 pages?
Yeah. Right. So I'll see you next week. Okay?
Thank you.
Thank you.